line bundle, ample line bundle over it, we ask the question, when does such a manifold have a Kahler metric in the cohomology class corresponding to the line bundle of constant scalar curvature? So this is a very general question about which not a great deal is really known in a definite way. This important special case is when our line bundle is either the canonical bundle or the dual of the canonical bundle of the manifold. And in that case, this constant scalar curvature condition is equivalent to the apparently stronger condition of having a Kahler-Einstein manifold with the Ricci Ricci curvature being a constant multiple of the metric. So these Kahler-Einstein metrics are better understood. In particular, is well-known older results going back to the 1970s of Oban and Yao. In the case of negative Ricci curvature, then these metrics always exist and are unique. The harder cases of positive Ricci curvature, which corresponds to, in algebraic geometry, to having what's called a Fano manifold. And then there are well-known examples to show that these metrics don't always exist. And the long-standing conjecture in the field, going back to Yao, is that there's a criterion for having one of these Kahler-Einstein metrics on a Fano manifold involving some algebro-geometric notion of stability, which we'll come back to say a little bit more about precisely what this is later, but the point is it's something formulated in terms of as the algebraic geometry of this polarized manifold. So there are similar conjectures that have been made and discussed in the case of, more general case of constant scalar curvature for general polarized manifolds. And there are, in fact, various sort of different definitions of stability that one can consider. And in particular, there's a relatively recent new definition given by Gabor Zekalidi, which is an important advance and which we'll come back briefly to talk about later. So still in the background, in the last year or so, working with Su-Shong Chen and Song Sun, we gave a proof of this Yao conjecture, a form of it, in the case of Fano manifolds. So a Fano manifold admits a Kahler-Einstein metric if and only if it satisfies a precisely defined algebro-geometric stability condition. So to be completely precise, the direction saying, sorry, I got the arrow in the wrong way around. Got my technical. The other direction, saying if you have a Kahler-Einstein metric, then it's stable. In the version of stability we want to use here is in fact due to Robert Berman. So this again is background, because I'm not going to talk directly about this result in this talk today. I have given quite a few talks about it, various places over the last year or so. So what we're going to talk about is some somewhat different but related statement. So let's consider some algebraic family, initially of Fano manifolds, and let's make the restriction that they all have finite automorphism groups, just to rule out some technical problems. Then we can look at the subset of this family. So sigma is our parameter space. We can look at the subset sigma prime, defined by saying that a point isn't sigma primed precisely if the corresponding variety has a Kahler-Einstein metric. Then it's very well known and standard and easy that this subset is open in the classical topology. It's open as in the standard sense. So the result we're going to discuss is that, in fact, this subset is a Zariski open subset in our family. So it's the complement of a finite union of algebraic subvarieties. So this is in a sense a weaker result than theorem 0 in the previous page, which gives a precise, in principle, a precise description of precisely which manifolds have these metrics. But it's a statement I like. For one thing, in the present state of knowledge, in practice, it's very hard to decide if a manifold satisfies this stability condition. So at least knowing that the existence of one of these metrics is, in a sense, an algebrogeometric condition, that's what this Zariski openness statement is expressing, is kind of a valuable thing to know. In any case, this theorem has in fact been proved by Yuji Odaka recently, the proof in this paper on the archive, using theorem 0 as a consequence of the, in a sense, harder theorem 0. But what the point of this talk is to explain a different proof of theorem 1, which is, in a sense, simpler and more direct, and also uses somewhat different techniques. In particular, in the context of this meeting, it uses techniques related to determinant line bundles and asymptotic analysis and other topics which Jean-Michel Bismut has contributed enormously to. So that's what we want to explain today. So let's get some further kind of motivation to make a technical level. The arguments in the proof that I referred to of theorem 0, they use a lot of technical material. I'd say they're rather lengthy, they use a lot of different technical material. For example, technical results from pluripotential theory and involving studying metrics with cone singularities. And all that is avoided here. Another point is, in a sense, negative, that the proof we're going to describe was, in a way, it's a failed proof of something like theorem 0. It's an incomplete proof of something like theorem 0. There's an approach to that, which I'll explain, but an interesting difficulty arises, which I want to kind of draw out. In a more positive direction, a point here is that although we stated the result in this Kahler-Einstein situation, many of the arguments, many of the core arguments, apply to the more general situation of constant scalar curvature metrics. See, although we've said that in the particular case of, say, Fano manifolds, or these equations are equivalent, they're very different as PDEs. So if you, in local form, local coordinates, so you'd be describing your metric as well known in terms of a Kahler potential. And then a crucial thing would be involving the kind of Monge-Ampere expression, taking the determinant of this. Let's call it say J, this determinant of this complex Hessian. So the Kahler-Einstein equation in local coordinates would be an equation that's something like J is equal to e to the plus or minus phi, a second-order partial differential equation of Monge-Ampere type. Whereas the constant scalar curvature equation would be a much more formable kind of thing. It would say that delta of log J is equal to 1, where this is the Laplacian defined by, it's called delta phi. This is the Laplacian defined by the metric phi. So you don't even have control directly of this nonlinear expression, this Monge-Ampere expression, when you're studying this constant scalar curvature equation. So that's related to going back to what I say, that these pluripotential theory techniques are really things that operate from the complex Monge-Ampere set of ideas. But so we're going to avoid these in the approach we're going to describe. So in fact, in this direction, a more precise statement in the direction of generalizing to constant scalar curvature is supposing we're in just the same situation as before, but now with a family of polarized manifolds, not necessarily Fano manifolds. Again, we can define a subset sigma primed. So supposing we happen to know two things. One is that for all these constant scalar curvature metrics, in fact, the Ricci curvature satisfies some fixed bound. And also, the diameter of the manifold satisfies.
This metric which is supposed to exist. Right?
Yes, so inside the subset where they exist. Yeah. Supposing inside the subset where they exist, we have these two fixed bounds.
No, because here, Ricci, you don't say this of this metric. I mean,
Ricci of this, yes, of this metric. And so the diameter of this metric. Then we have the same conclusion. So, of course, in the Kahler-Einstein situation, these are, well, the first one is by definition, because the Ricci curvature is a fixed multiple of the metric, and the second one follows from Meyer's theorem. Well, then, in fact, you have a positive Ricci curvature because you're bound on the diameter of a Riemannian manifold. So this is a generalization of the previous result. It's really only of theoretical interest because there's no situation I know where, apart from the Kahler-Einstein case, where we would know that these hypotheses are satisfied. And certainly looking at the second hypothesis, there'll be many cases we know where it's definitely not satisfied. For example, if we're looking at moduli of Riemann surfaces where we know that we can develop in a family long cusps. We won't have a bounded diameter in our family of...
You need two-sided bound to each, not one-sided.
That's what we need. And extending it to a lower bound would be perhaps possible.
True if you replace it by lower bound to each.
Well, I suspect it's true in general. I'm just saying that all we can prove is using these.
Conjecture is true. He's lower bound to each instead of the.
Well, yes, I would conjecture it's true without any hypotheses that anytime we have a family, the ones that have a constant scalar curvature metric are Zariski.
But this you don't require constant. This theorem you never say constant. You don't say.
We're saying it's constant scalar curvature. Sorry, maybe I didn't say this. If we have a constant scalar curvature metric, we would expect that in fact this is always true, but we don't. That is very far from being able to prove that. But under these extra hypotheses, we can prove it. And although I mean, it could be that in reality there are situations, even though we can't prove it now, where these hypotheses hold. Or perhaps more usefully, at least this sort of points that one would like to work at the proof and maybe extend the ideas to remove or reduce these hypotheses. Okay, so these are the results we're talking about today. So I'm going to try to outline the arguments, but I'll have to be quite sketchy about many things, obviously, to get through, to give an impression of give an overall impression. So there are three kinds of discussions that come together involved. One is in algebraic geometry. One is in what you might call Hermitian projective geometry. It's to say the geometry of projective space provided with a fixed metric. And the other one involves differential geometry and asymptotic analysis related things. So I'm going to spend a bit of time talking about these three things and then try to indicate how they come together. So let's supposing we fix a projective space, so we fix a degree, we can look at all varieties of a given dimension of that degree in projective space. And this is something which can naturally itself be given a kind of a complex algebraic structure. To fix ideas, in the most classical case, perhaps you think of the curves in three-dimensional projective space of a fixed dimensionally one, and you have the degree of a curve, the number of times it meets a generic plane. So this, but the point is that this thing, which is called the Chow variety, is something upon which the projective group acts, or we'll take the group to be SLM plus 1. So stability, which I say there are various slightly different notions, but it has to do with the structure of the orbits of this group acting on the Chow variety. So let me recall that. There's it's called the classical Chow construction. If we have our curve in 3 space, then the generic line will not meet that curve. But there'll be a hypersurface in the space of lines upon which do, obviously just counting dimensions. So that hypersurface will be defined by it's a subset of the Grassmannian of the appropriate kind, and it'll be cut out by a polynomial. And the same is true, you can think about curves in 3 space, but the same is true with the right numbers for general dimensions. So if you have a variety, then you can associate it, a Chow polynomial, which will end up in a symmetric product of an exterior product of the underlying vector space, or more precisely in an irreducible sub-representation of this under the action of SLM plus 1. So we get, this polynomial, of course, is defined up to a non-zero constant. So what we get is a map, an embedding from this Chow variety into the projectivization of this huge general vector space. If the parameters d and n are quite big, this will be some vast space of tensors. So the definition of the most the classical, simplest perhaps notion of stability, the Chow stability for such a subvariety, is that if we take the map given by the action on the corresponding f, so we take a map which takes an element of the group to the image of f under it, then this should be a proper map. Then such a V is called Chow stable. And this is a part of more general geometric invariant theory to discussing vectors in any representation space, not this particular one. So this is a picture of our big space of tensors. This is our F. As we move in the group, we move out to infinity in the group, we have to go to infinity in our vector space. Picture like that. But one can detect this in by a certain numerical criterion.
No, proper meaning variously close. I mean proper in this context, meaning it's ordinary variously close, but you don't want topology, right? You don't really are using usual topology.
Oh, unusual topology. I think
Unusual
I just mean I think I just mean a proper map in the usual sense. Yep. So we can detect this by considering.
It's not truly algebraic geometric condition, right? Because use topology.
Well, it ends up being. I mean, maybe there's a different language to describe it algebraically, but I think that's the correct definition. So we can detect this in a more practical way, in terms of a one-parameter family. So if we have GT, which takes to be a holomorphic function on the punctured disk, but meromorphic when we extend to the whole disk in SLM plus 1, then we can move F by this family GT, and saying that this is proper says that as we go over t equals 0, for all possible g's, we have to go out to infinity. That's to say, we have to definitely have a pole in some component of this tensor GT of F. So more generally, we can define a numerical invariant if we have this GT and F, called the Chow invariant, we'll call it, by saying it's the largest order of a pole of all the components. So that the stability condition becomes this numerical condition that's saying whatever GT we choose, this number should be positive, if it's not trivial, of course, not a constant map. Now that's a picture formulated in terms of the space of tensors, but we can formulate it also in terms of families of varieties. So to say we consider a family over the disk, perhaps we should call it a flat family or something, where each fiber is embedded in projective space, so the whole thing is embedded in the product. But we suppose that for non-zero parameters t, the fibers are all isomorphic to this fixed model, but for t equals 0, they could be something different. And this essentially, such a thing essentially corresponds to choosing one of these functions gt we were considering before. So what does this numerical criterion become? Another way of thinking about our Chow construction is that if we have our variety, there's a line called the Chow line intrinsically associated. It's just the line of possible choices of your F. So in this situation where we have a family of varieties, we get a line bundle over the disk in this way. But this hypothesis that all the non-zero fibers are isomorphic means that this line bundle is trivialized over the punctured disk. So it has a well-defined degree, and that is just this integer expressed in a different way, the degree of the Chow line bundle over the disk. And in fact, one could express this essentially a formula of I think Mumford and Knudsen-Mumford, I think, but actually the formula is not precisely right. But there should be a factor of d, the degree, in this denominator here. I'll leave you to put that in. Anyway, there's a formula for this number in terms of more familiar things. What we can do is we can take let L be the hyperplane bundle of the total space. We can take the direct image of that in the algebraic geometric sense to get a line bundle. Well, to get a sheaf, which we can take the first Chern class of, say it that way, on the disk. Or we can take the first Chern class of L, take it to the top power to get a cohomology class, which we can take the direct image of. And there's a formula expressing this number as a combination of those numbers where in each case we're using this trivialization of the punctured disk to interpret these things as integers. So we define Chow stability, which is involving just varieties in a fixed projective space. If we have any polarized manifold, X and L, then for any power k, we can take, well, sufficiently large, k, we can take the embedding in projective space defined by the sections of L to the k. And we can apply this notion. So the definition of stability that we referred to in Theorem 0, which is actually called k-stability often, the basic thing is you need to combine this sort of Chow idea with, we want also to consider taking the limits or asymptotics as k goes to infinity. So well, all we'll really say about that is to say we can define the Futaki invariant. And what we do, we take this Chow construction, but then we can do it. We can embed by, rather than taking L, we can take L to the k. So we can just embed this family not in the projective space we started with, but in bigger and bigger projective spaces by replacing our line bundle by the powers, and then we can take this formula, and essentially by applying Riemann-Roch to this formula, you see that, if I read that right, which I didn't quite, but then this resulting thing has a well-defined limit as k tends to infinity. And this is, it's called the Futaki invariant of the family. So let's go on to Hermitian projective geometry. Supposing we go back to a variety V in Pn, but now think of Pn as having a fixed Fubini-Studi metric, or the underlying vector space as having a fixed Hermitian metric. So we're going to define an object M of V, which is going to lie in the Lie algebra of SUN, n+1. By this formula, we're going to find a matrix. The alpha beta entry is given by taking this integral where Z alpha and Z beta are supposed to standard coordinate functions. And the fact we have the denominator means that this is well defined on projective space. And this measure is the standard measure induced by the Fubini-Studi metric on our subvariety. And then finally we take the trace-free part of that. We project that into the special unitary. So don't have time to explain all the significance of this. But sort of the significance of writing this thing down is that this represents a moment map for the action of this unitary group, special unitary group, on the Chow variety with respect to a certain natural.
Which Chow? Because there is no specificity degree not indicated here. Which degree? Because degree is absent from this formula. Chow has some degree, right?
Yeah, well, right. This is on any Chow variety. We can do this for any degree.
For all degrees, because they're very different dimensional spaces. Very different spaces.
Right, but whatever. I mean, but it makes sense for each Chow variety. But we're not really. This is a remark. We more eventually just think of this as a formula we write down. Okay. If we're given a V. But it's a fact that for any Chow variety, then you can interpret this as a moment map. So another way of saying this is that if you think of projective space as a co-adjoint orbit, so embedded inside this Lie algebra, then what we're doing is we're just taking the center of mass of V inside the Lie algebra, thinking of V in Pn inside this Lie algebra. In any case, the importance of this, the relation with what we said before, this one has the following inequality. Supposing we have this family, as we were considering before, we can extract from this always we can say it in a naive way, we can write it in this form by a basic factorization theorem, so in terms of invertible matrices and a matrix T to the A, where A is Hermitian. So we could diagonalize A, but then T to the A would just mean, would just be the obvious sort of diagonal matrix with T to the lambda I. What do we mean by that? Yeah. So we can always write our families in this form. Then, and we can suppose A is Hermitian with respect to the given metric. Then we have this inequality relating this Chow invariant to the pairing between the generator A and this moment map applied to the V0, which is supposed to be the central fiber of our family. So the more familiar case of this is when L equals R equals 1. So we're just considering G of T as T to the A. We're just considering a one-parameter subgroup. And in that case, in fact, one gets equality. In that case, we have a C-star action on the whole of our space V, and one can evaluate these cohomological pairings that we defined by using a localization principle to reduce them to the central fiber V0, and then this is exactly the formula you would get out. In fact, the different notation, if we let, if we have this diagonal matrix A, if we let H be the standard Hamiltonian for the generating this action on projective space, then this pairing we wrote down between M and A would just be the same as taking the integral over V of the Hamiltonian times the, with respect to this induced Fubini-Studi measure. This is a familiar kind of formula that arises in localization theorems in equivariant cohomology. Oops, what have I done? Where have we got to? It's important for our purposes that we don't want to restrict to this particular case of equivariant families, although it's the more standard case considered in the literature. The third ingredient, let's suppose now we have a constant scalar curvature metric, and that the hypotheses of the extra hypotheses on a bounded Ricci curvature and a bounded diameter apply. So let's consider what I call the Tian embedding. That's to say, we consider the standard embedding defined defined by the sections of L to the K, that's large enough K. But we think of this as having a Hermitian metric just given by the L2 norm on sections. So all we're doing is we're thinking of this as a Hermitian projective space. So the crucial point in this direction is that this is the main estimate in the talk, is that if in this situation we take this M applied to the tk of x, the image, we take the norm of this is just a matrix. We take the norm, the one norm where.
Yes, what is tk? Sorry, what is tk again? How is embedding from tk?
It's just the standard embedding given into this projective space.
H0, okay.
Yeah, assuming, of course, that k is large enough. But my point is that we're emphasizing this is supposed to have a fixed metric on it. And this is the L2 metric on sections. So we consider the norm on matrices given by the sum of the moduli of the eigenvalues. That's another way of saying it. Then that norm of this thing satisfies a fixed bound, where this could be expressed in terms of the constants in our principle various constants, but it decays like k to the minus 2 log k. That's the crucial. So let's just leave that as a black box for the moment. The second fact is that supposing we have one of these constant scalar curvature metrics and we consider a degeneration of it, call it x, then this Futaki invariant is always positive. So let's just leave those for the time being and come back to them.
Does it matter that you take the L1 norm there, or another norm might work as well?
Another norm might work, perhaps, but the proof definitely uses this. I think I don't know how to prove it for another. Well, I don't think so. That's an interesting question. So let's try to get to the main point, in a sense. So what we like, we're trying to prove the Zariski openness statement, but supposing we were trying to more generally understand if we have supposing we have some family of these polarized manifolds, and we know that at least some of them have constant scalar curvature metrics, and we're trying to understand whether all of them do, or particularly we're trying to say, what is the closure? We're trying to describe the closure of that space. So we have a sequence sigma I, we're considering a limit point. So we can fix some k, and we can consider mapping our x's by this map into a projective space, which means the same fixed projective space. And so we have, this is supposed to be a picture of the Chow variety, and the orbits of the SLN action on it. So what we can always do is, taking a subsequence if necessary, we can always suppose that these things, for each fixed J, converge to some kind of limit, say W. WK. Whereas we have some other sequence, if we just took our some basic normalized family, we'd have some other sequence, xi, which converge to our x, say sigma infinity. So we want to understand the relation between this thing, which is an element of our family, and this limit we get when we apply this action of this group. So there are two main problems. One is that this WK might vary with k, in principle, in the definitions. The other is that, which is what I want to emphasize here, is that this WK might not itself lie in the closure of the orbit of this x sigma infinity that we're supposed to have in our hands. And from the point of view of this discussion of stability, it really points in the closure that one has access to. But this WK could be something quite different, because these orbits you could have a family of, you could have a picture of these orbits which split up into, according to the picture shown. So you can't, from the fact that you have this sequence here, version of this one, you can't say that this limit is in the same orbit as this one, because you have this phenomena that orbits can split up in the group. So the most simple example would just be to think of the action of, say, C star acting something like this, where you have these hyperbola split up into the pair of axes as you go to the limit. So these are those sort of difficulties in trying to understand what we know about the limits from the algebraic point of view, the limits of these these subsets sigma primed. So since the first one is, in a sense, the more major difficulty, and this can be handled using, as I proved myself and Song Sun about a year ago, which is also fundamental in the proof of the theorem 0 that I mentioned at the beginning. So let me not go into that now. It's, using the fact that you can suppose that this sequence of manifolds has a Gromov-Hausdorff limit under the hypotheses that we stated, for example, this is where finite diameter would come in, then, so rather involved general results, one can essentially reduce to the case when all these W's, WK are isomorphic. So we get the same limit, whatever value of K we take. So to handle 2, so this is where we're going to go to our Zariski open statement. What one can prove, just plausible, is that there's a certain Zariski open subset of our non-empty, Zariski open subset of our parameter space, such that the orbits in the Chow variety have the maximal degree. So they're not the ones which are split up into smaller things. And more technically, that any degeneration of if we have a degeneration of a point in here, and we have of course, a family, say it's an arc running through there, we can always deform that degeneration to, so any nearby one, we have a nearby arc running through it. Whereas what we're saying is that we're considering the things that have got generic degenerations. They don't have degenerations which are not shared by the generic element of our family. So if we were thinking of an analogous discussion of where we're replacing varieties by rank 2 bundles over curves, it's well known, then degenerations would correspond to subbundles, and the analog of this sigma naught would be just to consider essentially bundles that have generic subbundles, only the class of subbundles that are present in the generic element of the family. So given all this, then, to prove our theorem, what we need to show is that if we have a sequence in sigma primed, supposing they converge to a limit point in this Zariski open subset, then the limit, this limit also lies in sigma primed. I was to say, in the limit, the limiting parameter, we have a Kahler-Einstein constant scalar curvature, which is a metric on the limiting variety. So I've written the proof. Here, let's draw the picture on the whiteboard. So this is some embedding of our x sigma infinity. We have our wk. Let's call it w. There are two cases. Either w lies in the same orbit of x infinity, which is the limit of our t of x. Then one can prove that in fact we have a constant scalar curvature metric in the limit. You can prove that in fact this sequence of metrics converges in C infinity as we go to the limit and defines a metric on the limiting variety. Or they could converge to a point in the closure of x C infinity, but then we can access that by one of these, an arc in the orbit, or that's to say, make it the central fiber of a family, of a degeneration of the kind we've been considering. So then we can do this for all k, and we have essentially the same central fiber, we have the same algebra geometric picture. So on the one hand, if we estimate this Chow invariant for this family, that's given by this pairing, what you can prove is that the operator norm, which is dual to this one norm, of these generators A, K, that grows like order K. So what we have to do here is we have to multiply the K to the minus 2 log K by K, so we get K to the minus 1 log K. But the crucial thing is that this tends to 0 as K tends to infinity, so we deduce that the Futaki invariant of this family is negative. Remember, the definition of this Futaki invariant is the limit of this Chow. And we have this inequality, this inequality here. On the other hand, by our assumption, by our construction of this Zariski open set, this degeneration for sigma infinity can be deformed to a degeneration of the nearby values that do have a constant scalar curvature metric. So by proposition B, the Futaki invariant must be strictly positive. That said that if we have a degeneration of something where the general fiber has got constant scalar curvature, then we have this stability condition, the positive Futaki invariant. So we get the sum is that we get a contradiction to the assumption that this W lies inside the orbit, the closure of the orbit, but not strictly inside the orbit. And so I say, although the statement involving Zariski open doesn't mention any properties of stability, you see that the ideas involving stability are embedded in the proof involving the sign of these numerical invariants that enter. But by reducing to this Zariski open discussion, we can avoid this phenomena where we have the splitting of orbits, which is much harder to understand in this situation. So what remains then is to discuss these two black boxes, proposition A and B. So let's just be rather brief about proposition B. If our family was one of the ones, an equivariant family with a C star action, then this would be a result of stopper. In fact, it would be saying in standard language that if you have a constant scalar curvature metric, and if you have this hypothesis that the automorphism group is finite, then the manifold is K-stable. So the proof is quite involved. In particular, it uses the idea of blowing up a point, and a theorem of Retzo and Packard is saying that if you take the blow of a manifold constant scalar curvature, it still has a metric of constant scalar curvature. But let's not go into it. The proof of this generalization that we want is a variant of stoppers. And in fact, one can write this down in different ways. One approach is to use a much more general result of Zeclidi in this theory which I mentioned at the beginning, which, well, this gives a very general, more abstract algebraic basis for the whole discussion of stability based upon filtrations of this coordinate ring rather than these kind of geometric degenerations that we've been considering. In any case, Zeclidi proves a general theorem which one can apply to this particular result. Or one can give a more direct proof closer to stoppers. But let's get on to the main point, which is proposition A, because this is where the asymptotic analysis comes in. Remember, we're supposed to prove this under the hypothesis of constant scalar curvature. We're supposed to prove this estimate for the bound on this M quantity, this moment map quantity, in terms of the parameter K, the power of the line bundle we're considering. So time is getting on, but the key player in this is called the density of states function. So if we have our line bundle, Hermitian line bundle L to the K, we can take any orthonormal basis and we can define the sum of the, pointwise, the sum of the norm squares of those sections. And this doesn't depend upon the choice of orthogonal basis. So this is an intrinsic function on our manifold. So what's been well known for many years is that if we, and going back to Chan and then other versions to Zeldich and Liu, what we need, is supposing we take some fixed metric, any metric in fact, and then we consider this function, depending on k, then this has an asymptotic expansion as k tends to infinity. With the right normalizations, we can suppose that the expansion goes like this. Then the crucial thing, relating it to differential geometry, is that this first coefficient, A1, is half the scalar curvature. So this is where the scalar curvature appears in the most obvious way in terms of the geometry of sections of this holomorphic line bundle, or the asymptotics, as k tends to infinity. In all of this discussion, it's important to bear in mind that you can think of this power, k, which of course algebraic geometers like to think about, more in terms of Riemannian geometry or metric geometry. This corresponds to taking a length scale, the square root of k. If you change your line bundle L to L to the k, it corresponds to changing your metric form omega to k omega, which means you scale lengths by the square root of k. No, exactly, you just multiply by. This is a trivial, this trivial but important thing to say. So what, in a sense, what you can think of this, the fact that you get 1 here, you can think of it as saying is that as you scale, as you k goes to infinity, that corresponds to scaling your manifold up, so that locally it converges to a flat space. And so obviously, I mean, the limiting value, the asymptotic value, is given by the value for flat space, which is sort of 1, or essentially 1. And then you can think of the higher coefficients as saying, as you, what are the deviations, measuring the sort of slight deviations from the flat space to all higher orders. So there's a bit of calculation here that I'm going to skip through, because time's running. I want to get to the main point. The point is that we can express, we want to bound the norm of this matrix M of Tk. Let's express this duality by taking the pairing of that with some A. Then we can write that in terms of integral, where in terms of this Hamiltonian function that we considered before. So everything can be expressed in terms of this function rho. If you take the Fubini-Studi metric, turns out, more plus the pullback of the Fubini-Studi metric under this map Tk is given in terms of omega by omega plus k to the minus 1 dd bar of log rho. So in the end, this estimate you need to prove, after some simple sort of rearrangement of the problem, comes down to proving an estimate for this integral, where this integrand is something which vanishes if rho is equal to 1. So if rho is equal to 1, the Fubini-Studi measure would just be omega to the n, and we would get rho omega, it's 1 times omega to the n minus omega to the n is 0. So this is something which is small if rho is close to 1. That's the point. And we can express the integral we want in terms of it. So what we need is some kind of, when we have this sort of uniform estimate, which is actually going to be uniform over the whole family, not just for a fixed manifold. What we want is this kind of uniform estimate on rho, which is quite different from the asymptotic estimate for a fixed metric when you take k to infinity. We want to say something uniformly about rho over all metrics satisfying our hypothesis. So that, let's come to the end of that, uses some analysis arguments which founded on what's called the volume estimate, in Riemannian geometry kind of estimate. So this is something we could do for any Riemannian manifold. If we take a parameter r, then we can define subset omega R, which is a set of points, so a point is in the set if the Riemann curvature tensor has got size less than r to the minus 2 on the ball of center R centered at x.
You have X Riemannian manifold.
X is any Riemannian, yeah, any Riemannian manifold. So this is just, in our application, it's going to be one of our constant scalar curvature manifolds. But this definition makes sense. So what's that? Another way of saying that is if we take this, supposing our point lies in omega R, if we take this R ball, we scale it up to unit size, then after we've rescaled, the curvature is less than 1. So we have on a scale R, we have a complete uniform control of the geometry. And the other assumptions we made also control the possible collapsing. You don't have a very small injectivity radius, something like that. So coming to the end now, the point is that if we have an understanding of so the two things. Supposing we're in this set R for appropriate value of R, then we have good control on the error. If we write rho k is 1 plus eta k, I'm assuming for simplicity that the scalar curvature is 0 here to make the formulae simple. Then we have uniform control with some fixed constant c on up to all derivatives of this error term eta if we're inside omega r. So this is crucial, but it's on the hand the proof is not really the proof is really a matter of looking at the standard proofs for the asymptotic expansion and using a certain locality property that if we want to study this function rho in a ball of a certain radius, so first of all the k is related to r according to this sort of length scale point of view. The asymptotic, what happens to this asymptotic expansion on this sort of ball doesn't really see whatever's happening outside that ball. That's the crucial point. So provided you have a lower bound on Ricci, that's to say. That's all you need to know, which in our case we do. So in any case, what one gets, we have this, in terms of this picture with these omega r's, we get some uniform control of this error term in the expansion. But then the harder thing is what wants is a control of the volume of the complement of this good region. So for each R, we have a good region, omega r, and the complement of the high curvature region. And what the crucial thing is to have an estimate on the volume of this complement in terms of r. And this is the r to the fourth is the appropriate power. So in fact, there are two quite different proofs of this, one given by Cheeger and Neighbor, really more from the Riemannian geometry point of view, and one by myself and Su-Shong Chen using the complex geometry to a greater extent. In any case, this is under our hypothesis. One can prove such an estimate, and then it's elementary to derive the bound we want on the integrals using these uniform asymptotic estimates in each omega r, elementary analysis argument.
So in this estimate, interesting, r goes to 0, what? Where this r goes where? I'm confused.
Well, this is for all r less than 1. It's interesting when r goes to 0, yes.
R goes to 0.
But it's true uniformly for all.
Yeah, I understand. Yeah, r goes to 0.
Yeah. It's a measure of the size of the high curvature set, or roughly, or the neighborhood of the high curvature set.
This is not the only bound of the volume. Yeah, volume maybe larger, but yeah, that's compact manifold or something.
Yeah, I mean, in our situation, we're supposing the volume, we're supposed to be in this fixed family, so we have a fixed volume. So I'm being a bit, so this applies under our hypothesis. But, so you can see that in one ingredient, the proof is quite long. All proofs are quite long, but one ingredient is the fact that under our hypotheses, we have a fixed bound on the L2 norm of the Riemann curvature tensor. So this comes from Chern-Weil theory, which is well known. So what that says, you see, is that if you look at the volume of the set where the curvature is bigger than r to the minus 2, then that's less than r to the 4, just by kind of obvious estimate of the integral. But this, what we're saying here is that, in fact, you take the R neighborhood of that set, you still have the same bound on the volume. Right, okay, so I've time to stop. So I've tried to kind of outline, so the point of this sort of analysis, this sort of asymptotic analysis is different from the kind of pluripotential Monge-Ampere analysis, which is used in the other theorem, the proof of the other theorem that I referred to. Okay, so I'll stop.